Total line was kind of long. That was like dude, if you're an accountant, pretty usual. So, but there's 5 million accounting places there. So.
All right.
Yeah, there was a lot.
So we're gonna pick up where we left off. Going to a new topic though. So to show you how to do that work in Excel, I put up the next Excel thing. It might not be set to release till after class today, but you'll have the next kind of connect homework as well. So I think originally I had a date for the exam is next Friday. It'll probably get pushed up a little bit to like that next week, either the Monday or Wednesday of that week. We'll kind of see where we're at the end of the day on Friday, and I'll kind of have make a decision based off of that. But getting closer to it, getting close to finishing up the material. Those homeworks, the Excel one is basically what we did yesterday. And it has a second part, which will probably cover Friday, actually. We'll kind of get through that and we'll be able to kind of tackle that whole thing. And then to connect, you can probably make your way through pretty much all of it by the end of this week, with maybe the last couple questions kind of holding up until next Monday. And then hopefully like next week, like maybe Wednesday and Friday, but Friday for sure, we'll do some review in class. I'll get some practice exams up this weekend for you guys to start looking at a little bit in advance of that. Sounds like you've got other exams you're worried about this week, so that's a little bit off in the future, but I just want to kind of mention where we're going. Yeah.
So when is the exams?
So definitely not going to be next Friday. I'll push it up to either that Monday or Wednesday of the following week. So it'll be what, the 20? No. I'll so those dates are tentative. Yeah, I think I say that. I think I'll say that right. But I'm pushing it forward in time. I'm pushing it like forward in time, not like closer to today's date. Right? Not bringing it forward. I'm pushing it forward, right, away from us. So I don't know if that's grammatically the way to say it. Probably not. My English is,
As long as we all are on the same page.
for being a native speaker of English, my grammar is terrible. But
English is hard. As long as we're getting more time.
yeah, more time. I'll never give you less time when it comes to like those dates. Okay? All right, so the next thing we're going to talk about, and it kind of combines what we were talking about with conditional probabilities last week. It pushes it a little bit further. It's going to be Bayes' theorem. So this stuff is not that exciting. The general idea of Bayes' theorem, it's been pushed to a point now. We kind of continue to take stats courses. There's a whole thing called Bayesian kind of statistics. I mean, this is a whole field. But the general idea is that you start out with a probability of something occurring. You run the experiment, you look at the results, and then you update your probability of that thing occurring based off of the results of the experiment. Right? So that's the general idea. We'll try to get, we'll revisit this idea once we kind of see how it mechanically works, right? But it's gonna have needs a specific setup. So we have to first have two states of nature. So this is S1 and S2, but you can think about it, it's some event and its complement. But it has to be something that only has two true states of nature. Right? So this could be like a disease, right? I have to run tests to see if you have it, but you actually have a disease or you don't, right? There is some true state of nature, and I might not be able to know 100%, right? But you do fit in one of those categories. So we think about these a lot of times, things with tests like HIV positive, negative, pregnant, not pregnant, guilty or not guilty, right? Kind of these outcomes where you either committed the crime or you didn't, right? There's only two true states of nature. So if these are there's only two outcomes, only two true states of nature, their probabilities would have to add up to 1, right? If I took all the people that were guilty plus all the people that were not guilty, that's every single person, right? So those, probabilities of those two states of nature just have to add up to 1. Now, we can't actually observe if someone's guilty or not guilty, right? We don't actually know if somebody is HIV positive or negative, right? So what do? We run tests, right? We run tests and look at the outcome of those tests to determine which of these true states of nature is in fact the true state of nature. So, I run this test, we'll call it E, right? The test either shows me, positive or negative in most examples, right? So the outcome E of being positive or outcome E complement that the test comes back negative. You can think about this in another scenario. I'm either lying about something or I'm not, You don't know, so you use a lie detector test. It comes back positive or it comes back negative that I'm lying. Well, they're not guaranteed though, right? These tests aren't 100% accurate. So even though I have these two outcomes for the test, I said last slide, let me set this all up, right? What I might be interested in is something like, given that the test comes back positive, right? Or comes back that the person is guilty, whatever the test outcomes are, given that I see a certain outcome on the test, what's the probability that the true state of nature actually is this first event? Or if I put this in the context of like an HIV example, given that I see an HIV test come back positive, what's the probability the person actually is HIV positive? Because we also know that when we look at the outcome of the test, there's going to be some maybe false positives, right? People will test positive who don't actually have the disease. Okay. So just because we see a positive test result doesn't mean 100% that the person has that disease. That probability, that conditional probability could actually vary quite a bit. And we'll look at some examples and see how it kind of can be counterintuitive. So, like I said, kind of the setup I'll have here is thinking about, testing some information. You can think about this as COVID, right? Or you either have it or you don't. We have these tests, they come back positive or negative. Some of them are better than others. In fact, if we have time, maybe I'll play around. I used to Google search the CDC and then try to come up with what these numbers are, but it's kind of similar to what we have for HIV. So I need, in order to find this conditional probability, I can try to rewrite it using the multiplication rule. And if I do that, I'm quickly going to realize I don't usually have that information, but I can rewrite it down to a point where I actually have those pieces of information, those probabilities. So I try to write out that conditional probability. So I see some outcome for the test. Given that, what's the probability to actually have the disease or have this state of nature? Well, I can rewrite that as the intersection of those two things divided by what I'm conditioning on. Now, in the context of what we're doing, the probability of E would mean what's the probability that you get a positive HIV test? Well, we usually don't know that. We usually know the probability you get a positive HIV test if you do have HIV, or we know the probability you get a positive result if you don't have it, right? We know the percentages of false positives and false, what would be false negatives, yeah, or true positives and false positives. But we don't know just the probability that if you give it to someone, not knowing if they have HIV or not, what's the probability that it comes back positive? I don't know that usually. So I'm going to start breaking this down. So the top part, I'm going to rewrite as kind of the conditional probability of these two things multiplied by what I'm conditioning. Right? Rewrite it that way. So I've got, that's my kind of, sorry. So I might try writing it out this way, and I realize that that's not helpful either. But if we remember that order doesn't matter, I can actually think about if I was to just flip these, like E and S1, I can actually find this using this conditional probability times what I'm conditioning on. So either one of these will give me that intersection. For us, what's probably going to be more useful is, I don't know the probability that the test comes back positive, but I know the probability that of the entire population about what proportion or what's the probability that they belong to this certain state of nature, right? And that they actually are HIV positive. I can look at historical data to kind of understand what that probability is. So we're going to use this equation to solve for that intersection. I can then break down, okay, the probability that someone gets a positive test result is really made up of two groups. People that have HIV and see a positive test result, plus people that don't have HIV and get a positive test result. Those are the two groups of people that I see get a positive test result. So I just broke it down to those two groups. Well, now I know I can rewrite the intersection as the conditional probability times what I'm conditioning on. So I'm just going to rewrite those intersections as conditional probabilities times what I'm conditioning on. And ultimately, I can start plugging things in, right? So I've got, I think the colors are off actually, right? This, blue and blue, and then kind of we can plug in green from up there. No, this is, this green should be up one. I don't know why I moved down like that. Need different versions of PowerPoint and started moving some of my images. So let's go here. I want this one, there we go. There you go. Now the colors should line up. There you go. So I'm just plugging things in based off this multiplication rule. And then this was kind of tricky, like to know that, okay, people get a positive test result. Those are two groups of people, right? People that don't have the disease and get a positive test result. People who do have it get a positive test result. Once I plug everything in, I've got this equation that I can use to now find certain conditional probabilities that I might have otherwise thought I can't find. So we're going to use this equation, but I think it helps to have some actual numbers, some actual example. So a couple things before we dive into an example with some values to it, right? Is that the probability of the two states of nature add up to 1. So we're going to talk about that. But also, if we look at the probability of getting the two outcomes of the test, as long as we're conditioning on the same state of nature, those two conditional probabilities add up to 1. So think about it this way, right? If I've got, given that someone is HIV positive, the probability that the test comes back positive, if I add to that given someone's HIV positive, the probability that the test comes back negative, we'll add to it. And we assume there's no inconclusive test here, right? We see some result, right? Well, this kind of makes sense. Given that I'm looking at just people with HIV, right? People who actually are HIV positive, they either get a positive result or they get a negative result, right? So when I'm conditioning on the same kind of group, right, or state of nature, those conditional probabilities for the two different outcomes of the test, they have to add up to 1. And so that's all this is saying, right? If I condition on the same state of nature, right, that the outcome of the test, E and EC, right, the complement, or seeing a positive and a negative result of the test, those have to add up to 1 as well. So we'll kind of exploit that a little bit. If we condition on different states of nature, it doesn't matter. All bets are off. Nothing really holds. We condition on different states of nature. There's nothing really advantageous that adding those conditional probabilities up will give us any insight in anything. Okay? So I'm using HIV tests, right? I actually can look at historical data and figure out the probability someone has HIV is about 0.006. Okay? So pretty small, right? Less than 1% of the U.S. population currently has HIV. I also know that over time, these tests that they've come up with to test for HIV are relatively good, right? If somebody, given that someone is HIV positive, these tests record a positive test result about 99.9% of the time. So I'm going to start writing out kind of what I have here every time I'm giving some additional information. So here, the probability that someone is HIV positive is 0.006, or we can think about this as our state of nature, right? Someone either has a disease or they don't. I'm then told, okay, the probability that you see a positive test result for someone who is HIV positive. So given that this person has the disease, the probability that the test comes back positive is 0.999. So there's a way you could set this up like a tree. I'll show you that in a second, but there's another way that I think is a little bit easier. So what I just said before is if I'm conditioning on the same group, I know that the two outcomes of the test, those conditional probabilities, have to add up to 1. So think about it this way. Once I've conditioned on something, I automatically know another probability right away. So what do I write in here? What other probability should I know? I'm conditioning on the same state of nature. Yeah, right. I should be able to come up with what the probability of the test is negative. Because if I have HIV, the probability I see a positive test result is 0.999. If I have HIV, then the probability I see a negative test result should just be what? Yeah, 1 minus that, right? Or 0.001. Right? These two things should add up to 1. I also was kind of, not explicitly, but implicitly given the probability of the second state of nature. If the probability that someone has the disease is 0.06, what's the probability they don't have the disease? Think about this as S2. The probability of the two states of nature, should add up to 1. So 1 minus 0.006 or 0.994. So anytime you're given a probability of one of those things of nature, you automatically know the other one, because you know those two things have to add up to one. And anytime you're given a conditional probability for an outcome of a test, you automatically know the conditional probability for the complement of the outcome of the test, right? Or the other outcome you can see of that test. Any questions on any of this? And like writing it out like this to kind of keep in group, I think makes it a little, that makes it a little bit easier. Yeah.
So when you read like the second bullet point, how do you know, like when you're doing a conditional, how do you know which one goes first?
So a lot more of the examples I'll use, like I would examine stuff, I explicitly use that terminology given, right? So here it's, the probability that you see HIV test record a positive result for someone who's HIV positive. So it's telling you like, the only way that I know that I see this positive test result is 0.999 is if it's for someone who actually has HIV. Well, you're right. The terminology I'll typically use if I'm examining cell and things like that. I would probably say it more like, given that someone is HIV positive, the probability that we see a positive test result is 0.9. Kind of using that given terminology, really identify.
Thank you.
Yeah, right. But it is like in practice more like you got to think a little bit harder about it, right? It's like people don't use that terminology a lot of times. You can grab these conditional probabilities; they're just phrased a little bit different. Good question. The other thing we could be given is the probability that HIV test records a positive test result for an HIV negative person. So they're given that someone is HIV negative. We know that the accuracy of these tests, right? The probability that you actually, this is actually, I get a false positive, right? But I see a positive result come back in that test for someone who doesn't actually have the disease. They're not, they're pretty accurate for identifying people who have HIV. However, they're also kind of pretty high in terms of, 1% is not that high, but there's a false positive 1% of the time. So automatically, I actually know the accuracy of this test, right? Conditioned on the same state of nature. I would actually know the probability that for an HIV negative person, if they take this test, the probability they get a negative test result would just be, we condition on the same state of nature. So those two things have to add up to 1. The two outcomes of the test, the condition on the same state of nature, those two conditional probabilities have to add up to 1. So we really were only given 3 probabilities here, but from those, we could identify 3 other probabilities. We may not need them, but just for identifying. So the next thing we might be interested in is, okay, let's say I administer a test at random, and I find that, was it a positive test result? Yeah, so that the test comes back positive. What's the probability the person actually has HIV? So what we want to find is, given that now the test comes back positive, what's the probability that the person actually has HIV? Well, it's a little bit trickier. Like it sounds similar to some of the things we're talking about over there. But now you're saying, well, no, I'm not able to observe whether or not someone has HIV or not. Like the true state of nature, I don't actually know. The only thing I can observe is a test result, right? Now, based off of historical data, I know that these probabilities exist over here, but all I'm seeing is a positive test result. And I know that positive test result could be identifying accurately someone with a disease, right? Someone who is HIV positive, but it also could be a person with a false positive, right? So, I see all these positive test results. Some of them will be accurate, some of them will be false positives. What's that breakdown, right? What's the probability that if I see the positive test result, the person actually has the disease? Okay. Right. So we can also build this out as a tree. Sometimes this helps people kind of, visualize it better than kind of writing it out and grouping it into groups there. You can think about here, the very first part of this tree will be, I'll just write down the probability of each state of nature. So my underlying state of nature that I can't really observe, like all I can observe are test results, is the probability someone has HIV, I was told is 0.006. So the other state of nature, the probability they don't have HIV, those two things on the same kind of row here should add up to 1. So that's another way to remember, like, oh, the two states of nature add up to 1. I then can think of about, okay, over here on this branch, I'm gonna condition on whatever the state of nature is. So HIV positive, I'm gonna come up with two conditional probabilities using that state of nature, right? I'm then gonna look at the conditional probability of each outcome of the test, right? So here I'm conditioning on the same state of nature, like this is like the HIV positive branch, here's the HIV negative branch. And then I have the conditional probability for the two outcomes of the test. And then I can kind of remember, they're on the same row and kind of on the same branch over here. So these two things should add up to one. And on the other side, here's my HIV negative branch. I condition on that state of nature. Look at the conditional probability of the two outcomes of the test. And then I know over here, this thing's on the same row, but on the same branch, these two add up to one. Here's a different visual. I'm kind of thinking about this. However you find it useful, if you want to set up a tree like this, you can. You want to kind of like write down what you're given and group them, like that. That's easy to think about using it that way as well. Okay. Any questions up to this point? We're getting close to being able to actually solve this. Okay? So how are we going to actually solve this, right? Well, we can go back. I've got everything that I was given plus additional stuff. I think instead of writing test equals positive, I just had it like P0S and negatives like NEG. I thought writing the test here makes it a little bit easier as I'm introducing this. So we've got what we want to look for, right? Given that the test comes back positive, what's the probability that someone has HIV? So all we're going to do is kind of go back to the general form. I'll write that out for us. Where is it at? There we go. I'm going to write out the general form of this equation, right, in the context of my example. So here, S1 given E. So my state of nature I'm interested in is being HIV positive, and the test result I'm interested in is that they come back HIV positive. So the probability of S1 there in the numerator would be the probability that someone is HIV positive times the probability of E given S1. Well, my E is that I see a positive test result given S1. So that was that the person is HIV positive. So really what this numerator represents, I might run out of room here. What this numerator represents is these are all the people that have HIV and got a positive test result. Right? So it's represented as a probability, right? But really what that is reflecting would be the probability of being HIV positive and getting a positive test result. That's what that represents, right? And that's kind of straight out of our multiplication. So if we want to, instead of thinking about these as probabilities, like that's what they will be. But remember, just like when we built those contingency tables, any probability, especially a probability of intersection, really reflects, right? At some level, there was a frequency calculated. It's just that we divided everything by the total number of observations. So really these probabilities do reflect like the number of people who have a positive test result and are HIV positive. And then what we're going to do is, the original idea was that we divide by the probability of positive test results. But we said these are composed of two different people. People who get a positive test result and have the disease, people who get a positive test result and don't have the disease. So that denominator, these two components represent those two different groups, right? So on top, I've got people that have HIV and got a positive test result. So out of the total number of people who get a positive test result, which, well, that's just going to be people who got a positive test result and actually had the disease. So notice the first part of that denominator is the exact same thing as the numerator, right? Because really what you're saying is, I know that this people who got a positive test result is composed of people who got a positive test result and had the disease and those who didn't. So that's like my total. But then, well, what's the probability then if I see a positive test result, the person actually has the disease? Okay, so out of that total, just whatever group you're kind of interested in here, it's people who actually have the disease. So the second part, right, we can finish out the denominator. The second state of nature, I ran out of room here, but if the state of nature 1 is HIV positive, state of nature 2 would just be person's HIV negative times the probability of E given S2. Well, E, the outcome of the test we're interested in was that the test came back positive given S2, which we just said was that the person's HIV negative, right? So we just wrote this out in the context of our example. Now it's the matter of plugging in our values. All right, what's the probability that someone's HIV positive? Look over there. 0.006, so plug that in here and here. Given that someone's HIV positive, what's the probability they see a positive test result? 0.999, plug those in. What's the probability someone's HIV negative? 0.996, wait, 994? Yeah. And then given that they're HIV negative, what's the probability to see a positive test result? I think that was the 0.01, right? Given that they're HIV negative, yep, the 0.01. So now we have all the values we needed. All right, we wrote this out in the context of our example. We plug everything in and we're done. All right, so we just plug in those values and it spits back out at me what this conditional probability is. Any questions over any of the steps there? You know, this is kind of interesting. So what this is really saying is, given that I see a positive test result, the probability the person actually has HIV is only 0.38. There's only a 38% chance that they actually have HIV, just if I'm looking at someone with a positive test result. And the reason why is because, well, look, this, like, the idea behind what we're doing in a way, think about it, it's almost like if we were to give every single person in the US HIV test, right? Then the people left that have a positive test result, right? Some of them are going to be our false positives, and some of them are going to be the ones we accurately identify. Well, there's way more people who actually don't have HIV, right? 0.994 relative to 0.006. So even though our false positives were only 1% of the time, we can almost put some numbers to this, right? And I'll do some really crude rounding when I'm doing this, but here's different consequences. So really what we're thinking about here is, like, if I've got 300 we'll use 300 million just to make it easier. So there's 330 million people, I think, in the US. We'll say 300 million just to make the number easy. So really what you're saying is less than 1%, right? Actually closer to like 0.5% of people, right, actually have HIV. So this would be something like 1.5 million Americans relative to the 200, right, 98.5 million that wouldn't have it. Yeah, because 1% of 300 million would be 3, 0.5% we got. So we're starting out to make everything testing. You think about, well, 1% of 298.5 million, right, is still going to be what? 2.98.5 million. So the number of people who are HIV negative get a false positive, that number will be a lot of people. Now, sorry, I should only do one decimal, right? So it's still going to be a lot of people. However, people that have HIV, we're going to identify almost all of them, right? So I mean, it's going to be a little bit less, but like pretty much 1.5, right? So if I'm thinking about this, how many total people get a positive test result? Roughly 4.5 million. So of those 4.5 million, only 1.5 million of them actually have HIV. So there are like numbers kind of floating around behind the scenes with these probabilities, because really all we did to get these probabilities would be take the frequency and divide them all by the total number of observations. So you can think about it in terms of numbers, and you know, that kind of helps you see, like, well, yeah, if not many people have this disease, even if the false positive isn't a very high percentage, we're going to end up with way more people with a positive test result that don't have the disease than people with a positive test result and have the disease. And so if I made every single person get a test here, right, without any symptoms of the disease, that positive test result is not going to tell me a whole lot, right? This is actually, I would argue, potentially there's a point at times with COVID where this has been the case, right? If you just tell everyone to get a test, you're going to end up with your positive test results containing a lot of false positive people, right? Now, if you start to do things like, well, now we're going to condition on, you know, do you have these symptoms and things like that, Well, now, we're making sure that we're not getting as many people just taking the test, because if I go out right now and I don't have COVID and I took 10 COVID tests, probably one of them's gonna come back positive. I mean, there's just the false positive, like here, 1% makes it look kind of bad. Some of those test special on are something like 10%, right? So if you just make everybody get a test, right, you're gonna end up with a lot of false positives, just in terms of the raw number. So this kind of highlights that, kind of a counterintuitive result, I think, if you told someone like, hey, if everybody in the US took a HIV test, because I go out and grab these numbers from actually the CDC and then some company that makes the HIV test. So these are roughly about what the numbers are. If everybody in the US took a HIV test, of the people that have a positive result, only 38% of them actually would have the disease, right? So I think that's pretty counterintuitive, but it is what it is, right? Things like this are good, right? If something's counterintuitive, we probably wouldn't have thought about it until we actually applied this and then we went to the mathematics. Yeah. I don't know that one. We'll use it. So I could also think about, let's say I had a true serum, right? So I'm going to eventually kind of make this a jury. But for now, think about we have this true serum, you can give it to somebody, and it makes them say that they're guilty, right? And it's hopefully like trying to make people actually confess to crime. So we're told that given that someone's innocent, if they take this true serum, it'll make them accidentally say they're guilty 1% of the time, right? So this is kind of like our false positive, right? This truth serum makes somebody wrongly confess to a crime when they're innocent only about 1% of the time. But we're okay with that because given that they're guilty, the true serum makes them say they're innocent about 10% of the time, which means we're accurately identifying or getting 90% of guilty people to confess, right? So given that they're guilty, the true serum makes them say they're innocent with a probability of 0.1. Given that they're guilty, the probability the true serum makes them actually confess and say they're guilty would be about whatever gets us up to 1 or 0.9. So we're like, all right, we're going to use this against all suspects that we have, try to get more people to confess. We don't have to go through this long, lengthy court process. And yeah, there'll be some casualties. It's not 100%, but we're okay with this as a society. Right? Let's just say that's what we've said. And then we're told, okay, of all of our suspects, 5% of them are guilty. Like we pull in a lot of people that actually didn't have anything to do with the crime sometimes. So if we give everyone the true serum, we're gonna have some people that are guilty, some are not, vice versa. But of the people we bring in, only 5% of them are guilty. So think about the underlying state of nature here is the probability that you're guilty or the probability you're innocent. You are one of those two things, right? You're not saying you're found guilty or innocent. I'm saying you either are guilty or innocent, right? I'm guilty of a lot of things I haven't been found guilty of, right? But I'm still guilty of them. So probability you're guilty, 0.05, probability you're innocent, 0.95, okay? So we've got our two states of nature. We're given two conditional probabilities. And we may have to do something similar that we did over here, which is using those conditional probabilities, we should know two other conditional probabilities as well. Conditioning on the same state of nature, we're looking at the exact opposite outcome for the test. Okay? So let's write down what we know. We've got the probability someone was guilty was 0.05, which made the probability they're innocent 0.95. And when you're writing these down, sometimes I'll shorthand this and I use like letters. You could write the words out. That helps make it a little bit easier for you. We then had, given that someone's guilty, the true serum makes it to their innocent is 0.1. So what other conditional probability would I know here? Yeah, given that someone's guilty, the probability the true serum makes them say they're guilty would actually be 0.9. Right? Those two conditional probabilities, condition on the same outcome, condition on the same state of nature should add up to 1. Over here, I also know the probability that given someone's innocent, the true serum makes them say they're innocent would be 0.99, right? I could come up with those probabilities ahead of time if I wanted to. I might not need those probabilities. In the last one, we didn't need the other two probabilities I came up with, but we could still find them just in case. So what are we looking for? Well, we want to know that given that a true serum made someone say they're guilty, what's the probability they're actually innocent? So if we were to employ this truth serum system, what's the probability, what probability of people we're gonna like wrongly be convicting, right? The truth serum made them say they're guilty, but they're actually innocent. Well, you look at the general form of the equation, like anytime we want to find S given E, right? The state of nature given the outcome of the test, right? We can rewrite this out in the context of our example, right? So our S here is being innocent, our E is the true serum made them say they're guilty or confess to the crime. So I just write this formula out in the context of my example, right? We go back to the general form of the equation. It was the probability of S, right? Which my S here is being innocent. And then E given S, the outcome of the test I was interested in is that they said they're guilty. E is still that they're innocent. Same, remember, the first part of the denominator is always the same as my numerator. And then the second thing is the probability of S2, the other state of nature, which would be instead of being innocent, being guilty. And then E given S complement, right? So someone saying they're guilty, given that they actually are. Okay. Any questions on that one? I didn't go through it as like, kind of showing you the general form of the equation like the other one, but it's the same sort of idea. Okay. So what does that numerator going to represent? We think about what we're looking for here. On the numerator here are people that are innocent and have actually wrongly confessed to the crime, right? That said they're guilty. Well, that's going to be out of the total number of people who just say they're guilty. Well, that's composed of two different groups. People who say they're guilty, but are actually innocent, and people who say they're guilty and actually are guilty, right? So it's like, oh, all these people that confess to crimes, what proportion of them were actually innocent? That's kind of what we're doing. But kind of the computational side of it is once we get to here, we're really just plugging in our values, right? Probably someone's innocent is 0.95. They're given they're innocent, they accidentally wrongly confess to the crime, 0.01. Probably they're innocent, 0.05, 0.01. Probably they're guilty, 0.05. I'm just plugging all the values I have in, but I'm left with one I didn't know. So this would be an example where I wasn't directly given the probability that given someone's guilty, the true serum makes them say they're guilty. I don't have that probability. But I'm conditioning on the same state of nature as I am up here. I'm just looking for the other outcome of the test. So that was where we said, given that someone's guilty, the probability the true serum makes them say they're guilty would be 0.9. Once again, my boxes are moving for some reason. I don't know if I'm using a different PowerPoint or what, but. All right, so I plug that 0.9 in, and then I'm done, right? So it's a little bit different if we have a missing piece of information. But if we just start out every problem, probably just like good rule of thumb, doing something like this, then we're never not going to have the probabilities that we need, right? Any questions on that? Okay, so we plug all those values in, we get about 0.174. So what if instead I had the same exact setup, right? But then I said, okay, given that the true serum indicates guilty, what's the probability that they actually are guilty? So what we found before was given that the true serum made them say they're guilty, what's the probability they're actually innocent? Now I want, given that the true serum made them say they're guilty, what's the probability they actually are guilty? Well, I could go through, right? I have a conditional probability, rewrite it out using Bayes' theorem. But what, right, if we found this was 0.174, what should this new conditional probability maybe be? Yeah, we'll minus that. So I didn't explicitly say this. It's a similar idea. If we condition on the same outcome of the test, so before what we were using to find those other probabilities was we were conditioning on the same state of nature. But it's the same sort of idea. If I say, okay, look, given that I'm looking at only the people who confess to the crimes, what's the probability that they're actually guilty and what's the probability that they're innocent? Well, they're either one of those, right? They're either innocent or they're guilty, right? So it's like once I'm conditioning on the same thing here, now instead of conditioning on the same test, or sorry, the same nature and looking at different outcomes of the test, I'm conditioning on the same outcome of the test, looking at the different states of nature. So as long as I'm conditioning on the same thing, whether or not it's the outcome of the test or the state of nature, kind of outcome, the other two outcomes of the test or the other two states of nature have to add up to 1. So before we found this was 0.174, so we don't have to go back through, write out the equation in the context of our example, plug the values in. We actually know those two things should add up to 1. So that would be what, 0.826 there. Now you could go back through, maybe do this one on your own, like reproduce and get that 0.826 by, if we hadn't have done this work, if we hadn't done this work already, right, then I would actually have to go through, write this out in the context of my example, plug in the values. Yeah. Oops, any questions on this? Getting there. So, this truth serum example is pretty goofy, but I use it because it actually has a pretty synonymous thing in the real world, which is just replace the truth serum with a jury, right? So if I think about, given that someone's guilty, what's the probability a jury finds them innocent, right? Or how many killers, are walking around amongst us. That's a weird way to put it, but you get what I'm saying. So, right. You also might have, given that someone's innocent, what's the probability that they're actually wrongly convicted? I mean, how many people are putting behind bars that we actually should? And then, maybe you're interested in, okay, if I could find these probabilities, which we kind of can in practice, because once we have historical data, I can go back through, especially since the use of DNA evidence, right? It's a lot easier to get an idea about, okay, given that someone actually was guilty, later on down the road, we actually know that they were guilty, but they were found innocent in the jury, right? We can also go back and look at the wrongful convictions. How many people's convictions were overturned? What probability, given that they're innocent, what was the probability that the jury actually found them guilty? So we can use some of this historical data and the introduction of DNA evidence to kind of get these conditional probabilities. Right? And then we might want to know something like, okay, given that I see someone in jail, right? Given that they were found guilty, the outcome of the test, the jury found them guilty, what's the probability of the true state of nature is that they're actually innocent, right? Well, if we have these conditional probabilities, we use some probabilities of just kind of underlying guilt and innocence of different crimes, we could actually back this out, right? And do a very similar thing as we did here. Just that we've got, instead of a truth serum, we have a jury, right? So what I used to have some pictures. Oh yeah. So given that you're guilty, jury finds you innocent, and then given that you're innocent, the jury finds you guilty. You might argue with me on either one of these, but I thought these were great examples. So then we would basically just be writing everything out in the context of a jury instead of a truth serum, and we can get at some of these probabilities, like I said, by going back through historical data. So this has this Bayes theorem has some real world applications. It isn't hard to find them, right? In a time of COVID right now, it has a lot of applications when you're thinking about test results and then false positives and the probability that someone actually has it versus not. So it has a lot of actual kind of real helpful uses. So that brings us to the next topic, which I don't think I'm going to start today. So what we'll start with on Friday is introducing this idea of random variables, discrete random variables. We'll probably also introduce the binomial distribution. I'll probably go through this stuff very quickly, right? This discrete random variables, the first few examples, I mean, it's very similar to what we were doing with the weighted mean and variance, but easier. And then we'll kind of transition to focusing more on that binomial distribution. And maybe if we have time, I might bring in some of the numbers of what it looks like for some of the COVID testing, and maybe have another Bayes theorem example I can kind of work through there. Any questions from me before we go on? We didn't use the iFocus today. Sometimes I won't. but probably will on Friday. So I will see you guys on Friday. If you have time to start taking a crack at those next homework assignments, get those out of the way so that you'll have to kind of work on them as we get closer to the exam. Okay.